Click the link in the description to download your own copy of this video's problem. Hey guys, Russ here. Welcome back to another fantastic chemistry video. And today we're going to be adding water across a double bond. Wait a minute. Not quite as easy as that, is it? There's a little thing happening here called rearrangement. We'll get into it. But before I do, please go ahead and slap that like button, leave a comment down below, subscribe to my YouTube channel. It really is helpful to all YouTube creators when you subscribe to their content. Helps us grow our channels, helps YouTube notice us, and promote us some more to the general public. Also, if you could please share my content with your family and friends or anyone that you know is struggling with organic chemistry. That really does help me grow my channel and does make me feel good that you think I'm doing a good job, that you recommend me to your family or friends. So without any further ado, let's get into this. So we're going to add dilute acid to an alkene. No problem. First step is always going to be protonation. Okay. So now bring out our dilute acid, which is essentially just some hydronium and water. Doesn't really matter what the acid is, hydrochloric, hydrobromic, hydroiodic, or sulfuric, whatever. It's just a little bit of protons and a whole bunch of water. Protonate. Now we've already learned about Markovnikov addition, so you know that the more stable carbocation is going to form. I'm not going to go into that. If you want to learn about that, there's other videos that I've done in this series that will teach you all about Markovnikov's rule and how to predict where protons will go in a Markovnikov fashion, i.e. there's no peroxide. Cation will be there. And let me draw this out so it's a little more clear. There, there's a methyl group there, just to make it more clear. Okay, now, water at this point can attack the carbocation. No one's surprised there, I don't think. Form the protonated alcohol, which will then be deprotonated by more water. Oops. Right, like that, to give you this secondary alcohol. Which, no problem. Pretty cool, huh? Which is this product right here. Okay, we're done. Not quite so fast. I've done the easy one. Tell me more about this one. This is the more interesting one. Okay. This is hard. It's not really. I'm just kidding. It's really kind of simple. It all stems back to here. It all goes back to this carbocation right here. Okay. So I'm out of space now in my working field, so I'm going to clear the board and come back and redraw some stuff. But we're going to basically start talking about this carbocation right here. So let me just clear the board. There we go. We've already solved for this product. Now we're going to solve for this product. Okay? So let me draw the mechanism of that reaction. And you're going to see some very strong similarities. Very strong. In fact, mostly the same. Only one key step. So far this should be very familiar, and this step should be very familiar. Just protonate the the alkene, protonate the double bond. You've done that 1,000 times by now, I hope. And let's draw out this carbon like we did before. And here's the blue hydrogen that came from the proton, or from the hydronium. Cation goes here. Okay. Now before we would have just attacked that with water and made this product here, called it a day. But we missed the most interesting product. So now remember, Whenever you form a carbocation, you have to always consider rearrangement. And that's what we're seeing here. We're seeing a rearrangement. We're seeing a methyl shift. So essentially, one of these 3 methyl groups here is going to migrate over to here or rearrange. Hydrogen shift, or pardon me, methyl shift. No big deal. So let's just draw this one here in red, CH3. What's going to happen is these electrons from here are going to migrate to here. Now why? Well, first of all, they're hyperconjugating, right? Remember hyperconjugation? If you don't, review it. It's an important concept. The hyperconjugating sigma bonds here are interacting with the empty pi bond, or sorry, p orbital here. So they're essentially drawing it over. Now, as this sigma bond gets drawn over through hyperconjugation, the carbocation starts to form on this carbon, and that's more stable. It gets so far drawn over this way that eventually the group just literally moves over to it, forming the carbocation on the tertiary carbon, which you all know is more stable than secondary. There's our methyl group from here. And now, let me just draw the other one in. And here's the other one. That came from here. And a plus charge will go there. Okay, so now everything past here should be very familiar. Water attacks the carbocation. To form the protonated alcohol, which of course will be deprotonated by more water. And that will give you this product right here. That's how you form that product right there. All right, guys, that's how you do it. That's the rearrangement part. That's the more interesting and maybe even slightly more difficult, but it's obviously the more interesting one. So make sure you know it, because rearrangements are something that we always ask our students about on exams. All right, guys, if you found this video helpful, please slap that like button, slap it again, because it really is helpful when you hit the like button for YouTube creators. Please subscribe to my channel. Please share my content with your family and friends, and please leave me a comment down below. Let me know how you're doing with organic chemistry. Let me know the kind of problems that I can help you with so I can fine-tune my channel just for you guys, all right? Now with that, I want to wish you all good luck and good chemistry. We'll see you soon. Email drbetts@protonmail.com if you would like a copy of every problem in this series.